In this video, we're going to examine the concept of the second derivative. So the first question is, well, what is a second derivative? So it's a lot more intuitive than one might think. It's the derivative of a function. So there are a few different ways to write this notationally. First of all, we can say that that's the derivative with respect to x of f prime of x. So basically, whatever our derivative function is, we're going to take the derivative of that. An equivalent way to write that would be f prime prime of x. So the number of basically apostrophes that we have here indicate the order of the derivative. So another way to write this is the order of the derivative is 2. So order of derivative is 2, meaning that that's the derivative of the derivative. Another way yet to write that is using this notation here, which, by the way, does not mean multiplication. D dx is an operator, so it tells us what to do with that function. So a more accurate way to describe that would be the derivative with respect to x of dy dx. Now this notation and this notation are just different ways of, this is called the kind of more of the a mix of the Leibniz notation and the Newtonian notation, and this right here is what we call the Leibniz notation, which is named after a mathematician that helped develop the idea of calculus. So this is where students often get confused. They see this is the most common way that we see the second derivative, or one of the most common ways, and most students want to read this as d squared y over dx squared. That's not how you read this. This is just a notation. Okay, that does not have anything to do with squares, no squaring, nothing to do with squaring at all, except somebody just decided that, you know what, this notation right here is a little less compact than we would like it. So my reasoning would be to say, well, first of all, they just thought they have a d and a d here, so they would call it d2y, and they had a dx and a dx, and they call it dx squared. I don't exactly know where that origin, the origin of the notation comes from. Lots of notations evolve over time, and so this is just one of those. So this is the same thing as just saying the derivative of f prime of x. It's just a simple way to put it. Okay, so what does it tell us? That's one of the most interesting questions that we would want to answer, is why would we want to take the derivative of the derivative? Do we just like taking derivatives a lot? Well, let's investigate a function. So this particular function has to do with the distance of an object from the ground. So in this case, we're measuring in feet, and we're looking at the height of the object, which is distance, the height, from the ground, measured in feet at t seconds. Okay, so it's basically as if somebody took an object up here, here's a person, and they're just dropping an object down from a building that is 16,000 feet tall. Or another way to be thinking about this is you have a skydiver who's jumping out of a plane, and everybody knows that I'm an excellent illustrator here. So somebody is jumping out of a plane from a height of 16,000 feet, and this tells us their distance from the ground, assuming free fall. Well, what I have here is just kind of our old notation of delta y, delta t, okay? So all we're implying here is that we're looking at how much does y, what's the change in y per corresponding change in t. Well, in this case, notice that the change in t is fixed at 1. The change in t is always 1, based on the way we've drawn this table. So the rate of change is really just the change in the distance over 1. And the change in the distance here, and I will go ahead and use these two cells to indicate that change. So we have a drop of 16 feet per second. Okay, and then the next second we have a drop of, let's see, 84 minus 36. That's going to give us, let's see here, 48, I believe, minus negative 48, or in that second, on average, you drop 48 feet per second at that corresponding rate. And then if we did the next one, looked at the next change in height, that one would be negative 72 feet per second. negative 80 feet per second. And then the drop would proceed in this fashion. And so here are the rest of those values. Now, if we look at how the speed is changing, so the question that we're going to answer here with this notation here, the change in the rate of change, so this is using delta because we're looking at averages instead of instantaneous, we're looking for the change in speed in that column. Intuitively, this is going to represent the difference between the speeds from 0 to 1 seconds and then the speed from 1 to 2 seconds. Well, that speed drops by negative 32 feet per second in 1 second. So a common way of writing that is negative 32 feet per second squared. Okay, that's again just one of those notations. We have seconds, feet per second over seconds, which is seconds squared, and the change actually is the same across all of these values in 1 second. And again, we have the same thing here, and we have the same thing here, and we have the same thing here, and we have the same thing. Oops, that's it. So we have a constant change in speed of negative 32 feet per second per second. Well, what is the negative 32 feet per second squared? This is what we call acceleration. Acceleration, and this is the acceleration due to gravity. So we assume, and we can test that an object accelerates in speed. Acceleration is an increase in speed, and that increase in speed is constant, 32 feet per second per second. Well, what is this graph? What does the graph of this function look like? If I were to plot it, it would look something like this. Now, of course, we're not looking at negative time, but if we were, this is what the function would look like. So this is telling me that the slope is becoming more and more and more and more negative. Similarly, if I went back in time, of course, this doesn't make sense in the context of the problem, a person falling or a person jumping from an airplane. The rate of change, what's happening to the rate of change over here? Well, first of all, it's positive, but then the rate of change gets smaller. So that rate of change, the change in the rate of change is negative, and the rate of change in the change in the rate of change is negative there. And the rate of change, basically, we're adding negative 32 to that rate of change every second. So what this actually helps us to do is that if I have a rate of change that is, first of all, positive, and then less positive, and less positive, if I keep subtracting from it, eventually that rate of change is going to become negative. Well, it turns out that the shape of this graph is what we call concave down. I'm not a big fan of mnemonics, but concave down looks like a frown, and that is kind of the shape of this parabola. Well, what if the change in the rate of change was positive? So let's suppose for a second that I started with an already negative slope. Okay, so that's just a little slope segment indicating a negative slope. So if we had a positive 32 feet per second, that of course doesn't make sense in the context of gravity, but what that would do is then the slope would become less steep, right? Because I'm taking a negative slope and I'm adding 32 to it, that is the change in the rate of change, and then I'm adding 32 to it and adding 32 to it, and eventually those rates of change are going to become positive. So this shape of the graph is what we call concave up. And an easy way to remember that is concave up like a cup, concave down like a frown, in case you just want to associate that terminology with something, so you can distinguish what concave up and concave down look like. And so what that drives us towards is the average rate of change has a very similar interpretation to instantaneous rate of change. Instantaneous rate of change is just at that moment, but average rate of change illustrates a lot of those same principles. So if the change in the rate of change, i.e., f double prime of x or f prime prime of x is greater than 0, then the function is concave up at that point. So that's going back here to having positive 32 feet per second squared. If, on the other hand, f double prime of x is negative, then the function is concave down at that point. So if we look at this function here, this function is concave down, and it turns out that the average rate of change is, the average the change in the average change in the rate of change is negative, and so that makes sense that that would correspond to something that looks concave down. So another way again to write this is just one notation, but we could also similarly say the second derivative of y with respect to x. We don't say d squared y dx squared. If that is greater than 0, that's the same thing as saying f prime prime of x is bigger than 0, or b squared, I said it, see? It's so tempting. The second derivative of y with respect to x is less than 0, then the function is concave down at that point. But what if the second derivative is 0? Because that is the only value that's missing in these first two bullet points. Is we have bigger than 0, less than 0, but what if it is equal to 0? Okay, like the first derivative, whenever we have a change in signs of the first derivative, this value of x is the value at which there is a change in concavity. It's called an inflection point or point of inflection. So let's look at a couple of examples. First of all, let's look at a concave up quadratic function. Okay, so if I were, first of all, to try to find the point of the concavity, what I would need to do is, first of all, find f prime of x. And f prime of x is 6x plus 4. And now f prime prime of x is pretty easy to find because it's just the derivative of this function here. And the derivative of 6x plus 4 is just 6. Now that's a positive 6, right? So if the second derivative is constantly positive, then that immediately tells me that the function is concave up. So that must mean that the function looks like this. And if what we remember about parabolas, if a is a positive coefficient, then the function is, in fact, an upwards opening parabola. Concave down, what about this function here? We know that this opens down based on what we've learned about quadratic functions, but why? Well, if we look at the first derivative of that is negative 4x plus 10,000. And the reason I picked these big coefficients is to indicate that it really doesn't matter what the coefficient of x or 4 is. Whenever you take the second derivative, the power rule applied twice ends up reducing the 100x term to 10,000x to 10,000, and then the derivative of that is just negative 4. And so if the second derivative is simply negative 4, then that means the function must just be concave down, like the way we would expect. What about a cubic function, though? Does that have, what do cubic functions look like, first of all? So from our experience of cubic functions, there are a couple of different ways these guys can look. One, they can kind of look like that, or two, they can kind of look like basically the reflection over the vertical axis. They can look this way. They can go from decreasing to increasing to decreasing. In this case, it goes from increasing to decreasing to increasing over here, and decreasing to increasing to decreasing over here. So if I were to apply the second derivative on this function, first of all, we know that f prime of x will be 3x squared minus 20x plus 12. And this will allow me to find critical points. But if I take the derivative of this function, f double prime of x, again, that's just the derivative of this function. So it's not like this notation should be scary or intimidating. We just have to figure out what f prime is and then take the derivative of that, which is going to be 6x plus 20. Well, immediately at this moment, it's not evident. Is this function concave up or is it concave down? A lot of functions can be a combination of concave up and concave down. For example, here, if we look at this function, then there's a portion of it that's kind of concave down right here somewhere. And then there's a function of it that's kind of concave up right here. It goes from increasing positive slope to negative slope. It's a concave down. And then negative slope to positive slope, concave up. So remember back here where we said, hey, you know what? If f double prime of x is 0, that is the point at which the function changes concavity. So we can figure that out. In other words, just like we set the first derivative equal to 0, we can figure out where the change in the rate of change is 0. And so that means that 0 has to equal 6x plus 20, which means that negative 20 equals 6x, which means that x equals negative 20 over 6. So this right here is possibly an inflection point. Okay, well, how do we determine if that inflection point corresponds to this graph here, going from concave down to concave up?